Is that video? Yep. It's on video, isn't it?
Is this that my email?
Yeah, why? How do you know that?
You said yes.
Did I? I've only just
So
come
he
up.
emailed you for how.
Oh, yeah. So I thought I'd video the lessons. I didn't realise I said that to you. Anyway, I hope you listened to that, Matt. Right. The book doesn't do this very well at all. You won't understand it, even if you're a physician, possibly. The book's awkward. It just throws in the big variables. It doesn't even tell you what they are, etc. However, the best way I found of describing this, I can't remember where I found it, and I don't know if it's from Martin Bamber or was it from Exam Solutions guy. I can't even remember, but it's a brilliant idea. You know the London Eye? There it is. So I'm going to draw. So if you notice, you're going to need to put this down. This will help you remember it. So tools, I'm going to need a circle, which is there. Okay, so it goes blah. Right. And tools and that. Now, I've got a centre there. And we're going to start the London Eye. We're going to start it in a horizontal situation just there, not that you would normally start there. Okay. Now, what happens to this carriage is it goes, as you know, round here, down here, and it's rotating. Let's pretend that it's all full now. You're not waiting for people to get on. It rotates at a constant angular speed. The angular speed, if you're not unaware, is measured as, or given the letter omega. Omega stands for how many radians you are moving per second. Okay, how many radians you're moving per second. Right, so at some stage I will move from there, I will move to there, okay? And how far will I move? Well, if I'm doing so many radians per second, I need to times that by the time, how many seconds I do, it will tell me the angle I've moved. So here, to generalise it, the angle is omega t. Okay? Now, if I'm down here, I'm putting a straight line, so it comes into line, it is just the diameter of the circle. Okay, one end to the other. What it physically looks like is that you physically started here. And what it looks like now is that you're moving inwards. Do you agree? Okay. There is the centre of oscillation. And what it looks like is that this distance here, it is always, and that is the crux of it, it's always measured from the centre of oscillation, X we call it. But if I draw this here, at this stage here, this line is also known as, well, sorry, I would also here. That's the maximum. Sorry, I would just give you something else. That there is the maximum distance you can go out, which is the length of the arm. We call it the amplitude, A. Okay, so the length of the arm is A, as it's rotating around. That's the amplitude of the oscillations. As you're going round, what is that now? Now you can do it. It is, well, if I'm after adjacent and I've got a hypotenuse, it is A cos omega t. So that distance there is the distance here that you're measuring. So I'm going to put a dash there. That's where the particle is now, P, or particle. L-E or A-L? L-E, isn't it? Oh, screw that one up. It's embarrassing. Anyway, that's the particle, and we always measure from the centre. So that there is our X. Do you agree? Not from here. Even though we started from here, it is not that. You will want to put that in and you will get it all wrong. It is always measured as the X is there. Okay? So we can write down now, as you've just told me, that X has the value A cos omega t. Omega, is it constant or varied? In any given question? It's constant. Okay, that's a constant. T is the varying thing. A constant or varying? Constant. The amplitude is always fixed to what the amplitude is. Okay? And X varying or constant? Varying. Okay. Right. I can also look at it in this vertical sense. But if I'm looking at this vertical sense, the particle starts. So I'm going to put an arrow here and change my colour. Because sometimes you use one formula, as you'll see, and sometimes you use the other, depending on where the oscillations start. So we're going to say here, start. Now here, it looks like it starts in the centre. This starts at the extremity, and use this formula when it starts at the centre. Start. Now, the distance here, change colour. The distance here is again measured in x, so the particle is now there, it seems, and that distance is x. And x can be written as, that's it, so it's a sin omega t. Now it doesn't matter which one you use, it depends where you start. If you start here, then you're going to be using this. They're totally different measurements. X is different here as opposed to this one here, but it depends where you start the oscillations. Okay, so it doesn't matter which one I look at now. This works for either. I'm not going to do for both, but what I'm about to do now works for this or this. Right. The next step for getting the equations out, the whole idea of this is to get some equations out that we're going to use to help us solve problems. Now, what we do is we differentiate this with respect to t. So we get x dot, which is velocity, is equal to, and what will it give us if t is the variable? Careful. Minus a omega sin omega t. Okay? Right. Now, this bit isn't so intuitive, but it's obvious now when you see it, because sometimes you have to prove this. Right? So if I square both sides now, I end up with x dot squared is equal to, and square this, it becomes a positive, and it gives you a squared omega squared sin squared omega t. Okay, happy with that? What I'm going to do now is refer back to this, and this entire process works for this up as well. Okay, you'll get to the same results. Right, so here we go. If I rearrange this, I can see that if I rearrange it, I can see that I've got x over a is equal to cos omega t, and I can change this by using x dot squared equals a squared omega squared, and it is 1 minus cos squared omega t. Okay, that there is going to be replaced with this, which is squaring that. Okay, so therefore I now end up with x dot squared equals a squared omega squared 1 minus x squared over a squared. Happy with that? Times through by this now, or in fact times through by the a squared, just the a squared. You end up with a formula x dot squared is equal to omega squared a squared minus x squared, and I want that highlighted. That is the formula to find, edit, undo, that's the formula to find velocity when I know, what do I need to know? Obviously I need to know my amplitude, I need to know my angular speed, that's what that is, angular speed, and I need to know the distance. I want to know from O, that's the distance, David, that's the distance, that's where you're going to lose it, that's the distance measured from O. Okay, so remember that, that's measured from O. Now if I start here, I'm just pre-warning you, and I look at something here, then the distance is negative x. It's positive this side if I start here. If I start there, obviously that's positive, that's negative. Does that make sense? But it's measured from O. Okay? Right, and you can see that because when this rotates round, cos is negative in this quadrant here. Okay, when you rotate round. Right. My next thing, okay, the next thing is to look at this, come back to this now, and to get another formula. And that is the one for acceleration. If you differentiate that a second time, you get x dot dot, so you differentiate with respect to t, you end up with differentiating this now gives you, bear in mind these are constants, and it's going to give you what? Cos omega t. Okay? Right, and using the same thing here, I can see that cos omega t is x over a, so I can therefore write x dot dot is equal to minus a omega squared, and I'm replacing that with x over a. The a's cancel, and it leaves you with the last formula, which is really important. X dot dot is omega squared x. What does that tell you? I'm going to highlight it. Okay, what does that tell you about the acceleration at any given point? Okay, and where's the displacement? X is always increasing, is always going away from O, and therefore the acceleration is always heading at any stage towards O. Okay, because of this negative here. Right, remind yourself that's omega. That's just a constant. Okay, so it's proportional to its displacement at any given time, basically. Okay, everyone happy with that? Right. A couple of things I want to talk about now is if you come up here, I will look at these two equations. What is the what is the maximum that this can ever kick out? When x equals what? Where am I at when x equals what gives you the maximum velocity? Can you see that I'm going to make a note here also at this stage here? So max x dot when x equals 0. Right? If x equals 0, where am I? Or yeah, equilibrium or the centre oscillations, whatever you want to call it. So yeah, so therefore at O. Okay. So we always know if you've been given the max velocity, you can now use the formula. You wouldn't use, so don't write this down. Look, x squared equals omega squared a squared. Okay, it's pointless because what's that telling you? It's just telling you that. Okay, that will, if you're given and guaranteed that it's max velocity, use this. So use when given max max velocity. Say again.
Would it be plus or minus for the omega when it's at max velocity? Because it's square root. And it could be.
Well, yeah, yeah. Okay, so we're just looking at the magnitude there. Yeah, you're right. Okay, so yes, it's got direction to it. Okay, right. So that's that one there. This one here. When does you can see here that you got maximum acceleration, as in the magnitude of the acceleration. Okay, you're frequently just looking at the magnitude of the acceleration. The maximum acceleration is when x is maximum. Do you agree? And therefore, it's on the extremities, as I talked about the other day. So here, you can put an arrow down. Max acceleration is at max x, i.e., what's that? A. So x equals a. Okay, so this one was when x equals 0, and this one is when x equals a. And there's one last thing I want to talk about, and then we're away. Okay? And that is period. The period is talking about the time it takes to do a full oscillation. That is going from wherever you start, let's say start at centre, going to one end, back to one end, and back here again. No, sorry, start at centre, did I say? Yeah, there, and back to centre. Yeah? Does that make sense? So full 360 if you look at the circle, the eye. So if it's a full 360 rotation, then what will be the period, the time it takes? And we use, so put down period, it's the last formula, we use tau, that looks like that, is equal to, any ideas what the formula will be? It's a very simple thing. Don't give the game away, you lot, shut up. I've just given, it's in radians, obviously. How you work it out. How far have you got to travel? So 2 pi, that's 2 pi on the top. And what's going to determine how long it takes you to go round? 2 pi over, not t. What's t? Omega, okay? Omega is your angular speed. So that's radians per second. The second comes up. This is radians, so just give you seconds overall. So that's how many seconds it takes to do one period, one full circuit. And that's it. I want that highlighted. Okay? And those are the formulae. Okay? I also want you to highlight this one up here, because this depends. You will use this format to start with. This is your starting point. If you start there, you will use this one if you start there, and then we're away. Okay? Everyone happy?
Mm-hmm.
Any questions? Is that what it's like in physics?
Pretty similar, but we don't use differentiation, just give given formulas.
Well, that's wonderful. Just giving things, not knowing where they come from.
They sort of do, but we don't have to. You don't have to know it.
Anyway, here we go. Next question. Over. No, I need to go onto the board, don't I? Bang. Scroll down. Bang. Right. Get rid. Now this is all. I mean, it's just awkward to understand. I go straight into this formula without explaining where it comes from and what's going on. So forget